This media was gratuitously produced by Clear Contributions Audio Video. The intellectual property contained within belongs to Dr. Barbara Van Kyken. Clear Contributions. Let's have clarity.
I will go over this step by step with you, and then I'll just send it to you. I have one thing that I wrote out on the Word program, and then transferred it into Notability, and then took a bunch of notes on top of it. And I wrote it out wrong in Word, and I'm not that interested in going back and starting over again. So I'll show you that. Little boo-boo. All right, we've gotten to that point, right? All right, so as far as I can think, the reaction labels that apply, look at your list and figure out, because it's going to be hard to remember, I think. That's one of the reasons why I have you put a list on here. So the water, you're crossing off the hydrogens. It's present in high concentration. You're putting the electronegativity labels on it. The only feature really in B is the pi bond. And in C, the only feature really is the incomplete valence shell. And D, the only thing you really have are the partial positive and negative charges. And then E has a bunch of labels because you have the partial charges and then the positive thermal charge. But that wouldn't be present in high concentration because you've probably just put in, even if you didn't put in a trace amount of acid, you're not going to put in 55 molar of acid. So, any questions about that part? Okay, you don't have to color code the thing with the mechanism arrows, but I did just to help make it a little clearer for you. You're always going from electron rich to electron deficient, which means that you're going towards something that would be highlighted in green, let's say, to something blue or red, or a better way to think of it is towards the positive or otherwise electron deficient. So that could be a partial positive or an incomplete valence shell would be your most likely.
So it's going to go to the positive. Electrons are going to the positive.
That's right, because they're negatively charged.
Gotcha.
Yep. So opposites going together. Good morning. So on the first one, you're going from the pi bond to the partial positive on the hydrogen. The hydrogen can only have one bond, so you have to break it. When it breaks, it goes towards the thing that's pulling the electrons towards it in the first place, so you're breaking negative. On the next one, you're going towards the electron deficient carbocation because that's an incomplete valence shell, and so that's why I highlighted it in red. On C, you're going towards the bromine since that's an incomplete valence shell as well, but you only have one electron going, and so since you have two electrons in the bond, it means you have to have two half arrows to show where the two electrons are going. So that's the deal with radicals. You're going to have multiple arrows, where with a carbocation you only have one. And then in D, you're going towards the radical. Once again, since you have two electrons in the bond, that means that you have to have two half arrows, one showing that the electron ends up on the bromine so that you have the bromine radical, which I should put in here. Any questions about those? All right. This is the one that I goobered. Because I put the pi bond between carbons 2 and 3 instead of between 3 and 4. So I tried to make it a single bond and everything. It's not quite right. But anyway, there's no room to show all of the steps anyway, so it worked out right, or something. When you label everything in the first step, you want to put all of the labels for the reactants on there, and then identify what is the most reactive feature. So the most reactive feature in this go-round is the pi bond. So you think about what it wants. It wants something electron deficient to react with. Because you're reacting a pi bond, you're going to create an incomplete valence shell every time. This time you'd be creating a carbocation. So you want to think about which vinylic carbon you'd want to have the carbocation on. And so you identify with the numbers. Both of them are 2s, but the one has an option for a shift, so it's a special kind of secondary. So that's the one that you're going to put the carbocation on. Step 2 is write the reaction arrow so that you can show how the reaction occurs. It's going to go from electron rich to the electron deficient. That hydrogen then would have too many electrons, so it has to let go of the bond to bromine. And the next step, which I don't have here, you'd have a carbocation on this carbon. And so you want to label that carbon and anything adjacent to it as primary, secondary, or tertiary. And if you do that, then you notice that you have a tertiary carbon next door while that one is secondary. So that means that you're going to do a hydride shift because you have that option. And so this should have had a hydrogen on it, but I had a double bond there originally. So anyway, the bond for the hydrogen goes over and you end up with the carbocation on the tertiary. So I've got better examples of how to draw out the shifts and everything. Like I said, I can't erase this because I did it in Word, see? So I can't fix it, sorry. So that was step 3, look for a shift. Step 4, look to see if the products are stable, and they're not. You've got an incomplete valence shell there. So that means you got to list and label the reactants once again. Include not only that product, but any product from that first step, as well as anything that you didn't react in the first step. So the thing that's left over after the first step is the bromide. And that has a non-bonded electron pair. So that's what goes onto the carbocation. And so the step 5 is show how that goes towards the electron deficient. And then step 6 is figure out stereochemistry. This doesn't have any chirality centers because all of the carbons except one have multiple hydrogens, but the carbon that doesn't have multiple hydrogens has 2 methyl groups on it. Okay. On B, the most reactive feature is the bromine radical. That's a result of the peroxide breaking down. So that's the thing that's driving the reaction. You want to figure out what it wants. It wants more electrons. The source of electrons then would be the pi bond, since those are weakly held. Since you're going to create a radical in the next step, you want to label the carbons, the vinylic carbons. And you have secondary in both cases. Don't be thrown by the idea that you are looking at the neighbors now, because a radical can't allow a shift because the orbital is already partly occupied. So because you have 2 secondaries, it means that this time you're going to have to draw out both. The molecule isn't symmetrical, and you have equally good places to put the radical. So I only diagrammed out the arrows for one of them, but if one of the arrows goes from the pi bond to the incomplete valence shell, then the other half arrow has to go onto one of the 2 carbons to create a radical. So those are the 2 products that you would have depending on which carbon has the radical. So in the next step, you've got to analyze and see if that's okay. It isn't. It's a radical, so it's got an incomplete valence shell, so you're not done. So list and label all of your resources. You still have quite a bit of hydrobromic acid left over because you only have trace amounts of peroxide, which means that you have a trace of the bromine radical and most of the HBr hasn't reacted. So the reason why you don't pick the HBr in the first step is because it's not the most reactive feature. You're only worrying about the most reactive feature. But in the second step here, where you have the incomplete valence shell as the most reactive feature, now you're looking for what's present in the highest concentration, and so that's the HBr. Although you could put a bromine radical on there also, that does happen sometime. We're looking for the major product, and it's more likely to react with something that's present in a higher concentration. Do you have any questions about the radicals? Yes?
On this, do we have to draw it out with the hydrogen and then write our
And this is going to be really similar to the test. Write the major product for each reaction, and then the stereochemistry. So for the test, and I was running out of room here, and I knew I was going to have to show you in class, so I can't garbage it up a lot. But what I would want you to do for the test paper is then to draw each one of them with the hydrogen attached where the radical was as your product. And you don't have to show me all the steps. This is just to help you think through to get to the correct answer. So I'd recommend it, but I'm not going to grade on that. Yeah.
You're just looking to see if we have both those.
Yes, exactly. So both of those have a chirality center. Both of those have one chirality center that was created as a result of the reaction. So since both of them have one chirality center, both of them would have a 50-50 proportion of R and S. Any other questions about that one? That one's extra tricky because you ended up with two products. Okay, 3-methylcyclohexene. The hexene, the ene doesn't have a number because that's a functional group, so it has to get the lowest number possible, so it has to be between 1 and 2, and so then you figure out where 3 is based on that. It has water, which is present in high concentration, but the trace amounts of acid mean that some of the water molecules have an extra hydrogen on them, and so therefore the oxygen has a positive formal charge. However, the water is what's present in a high concentration. So if you label out all the charges, cross off the hydrogens, figure out the water has a high concentration. When you look that all over, the most reactive feature is the pi bond. That's driving the reaction. So you're looking for something with that's electron deficient to react it with. The only thing that you have there that isn't crossed off is one of the hydrogens on the hydronium ion. Step 2, show how the reaction occurs. You're going from electron rich to electron deficient. The hydrogen can only have one bond, so it lets go of the bond to oxygen. Step 3, once you've got the carbocation there, I actually had enough room to show it this time. You want to, thank you. You want to number the carbocation and then each atom directly attached to it and see if you have a larger number next door, because if you do, that means you could shift everything so that the carbocation has more carbons surrounding it. So you want to do a shift so that the carbocation ends up on the tertiary carbon. Because that carbon has both a methyl group and a hydrogen, and you want to keep as many carbons there as possible to keep the stability there, the stabilizing factor, you want to move the hydrogen over, so you show that by moving the bond from the hydrogen over to the carbocation. And redraw it. Is that kind of answering your question, Josh? Kind of, sort of. So because I move this hydrogen over, now that has 4 bonds. There's an implied hydrogen on here. Now that has 4 bonds, so it's no longer carbocation, but because I've moved this away, now that only has 3 bonds. But you show the movement with using an arrow that shows the electrons or the bond moving over. And you move the hydrogen, because otherwise if you move the carbon over, that becomes secondary now, and that didn't do you any good. All right, so step 4 is check the product. Oh dear, you have an incomplete valence shell, so that's no good. List and label all of the reactants you have left over from the last step or that you didn't use. We didn't use the water, and you created water in the last step. So essentially you have, oh yeah, water. But besides that, the water is present in a high concentration since it's a solvent. And the carbocation is so crazy unstable it will react with anything. It has non-bonded electron pairs. So show how the electrons go in the next step by going from the source of electrons to the carbocation. And then you can drop the hydrogen off. That's not a huge deal. Because the only potential place for a chirality center would be here. Because you have a methyl group and you have the hydroxide. But if you go this way, it's CH2, 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 CH2. If you go this way, it's CH2, CH2, CH2. It's the same each direction, and so therefore that's not a chirality center, so none. Do you have any questions about that?
What's the trick to learn chirality, non-chirality? I was a little confused with that. It's like chirality or no chirality.
Yeah, and you can go back to chapter 2. I've got some examples in there of when you have a chirality center of the cyclic compound and when you don't. But let's say that you had the same situation where you had like a CH3 and OH, but now you have something attached here. Then when you're going this way, you're running into a carbon with a bromine attached to it, and when you're going this way, you're running into carbon that doesn't. And so that makes the two sides different. So trace around from the point that you think might be a chirality center and just trace around and see if it's any different. And it doesn't have to be just the next carbon attached to it. It could be anywhere as you're tracing along, but it's, yeah, the idea is if it's different. However, if you had something like that, it isn't, because you're going CH2, 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 carbon with a bromine. You know, it's like you're running into the same situation each way you're going around. And since you have to have 4 different groups, the 2 groups sticking off of it are easy to picture. It's the other 2 groups are part of the ring, and so you just have to see if it's different. So in the book, what I said you can do is you can mentally disconnect this and see and consider that to be one group. And then you could also just do the same thing where you're mentally disconnecting this and, oops, too much, and then seeing about that group. But I think what might be easier is just taking your fingers, just tracing around, you know. Anything else? All right. This is a very similar problem. I just wanted you to have practice with a methyl shift, though, or an alkyl shift. Pi bond, water, the hydronium ion, the pi bond's the driving factor. You're choosing between a primary and secondary, so you're going with a secondary. The electrons go towards the electron-deficient hydrogen, which lets go of its bond to oxygen, and you end up with a carbocation. Since it's a carbocation, then you number the carbocation itself and the adjacent carbons, because the one to the right is got a higher number. That means you're going to have a shift. And because it's quaternary, it means you don't have the option of moving a hydrogen, so this is one of the few times when you actually move a carbon group over. So you show the bond unplugging and moving over a notch and plugging in, and then there's your new carbocation. Because it's carbocation, you got to keep going with the reaction, list and label anything that you have left over from before. Water's present in high concentration again. So that's, you always choose the carbocation resolution based on what's present in the highest concentration. Add on the oxygen, you can drop off the hydrogen there to get rid of the positive formal charge, and this doesn't have any chirality centers because the carbon that has the OH group has 2 methyl groups attached to it, and the CH that's just to the left of it has 2 methyl groups attached to it. So the only options that don't have multiple hydrogens have identical other kinds of groups attached to them. Any questions? I'm sorry, which are you talking about here?
Yeah. No, you did a methyl shift.
I don't have a hydrate here to shift, so that's why I was backed into a corner and had to move a carbon group over instead. So only do that if you have a higher number here, and you do an alkyl shift. There's only 2 cases. If this is a 4 and you don't have an option to move a hydride, or if the ring is really strained and you haven't really done a lot of practice with that. So. Good. All right. Trace of acid and ethanol. So this is going to be the same exact kind of thing. You have ethanol mostly present as just plain ethanol. And then you have some molecules that are acidified. And you have the pi bond as the reactive feature. And that is not a tertiary, that's a quaternary. Because you have the higher number there, then you do a methyl shift. You have an incomplete valence shell, so you look at what's present in the highest concentration from before. The oxygen just shares its electron pair, nothing else detaches at that point. Drag the whole molecule on and attach it. And then if you want to, you can drop the hydrogen off. This time you created 2 chirality centers. This is a chirality center because you have an implied hydrogen in a methyl group. And then when you go in this way, you have a carbon with all that garbage attached to it, and this is a CH2. So that's a chirality center. This is also a chirality center because you have this and the methyl group, and then when you go in this way, it's a CH2, and you go in this way, it's a carbon with the methyl group attached to it. 2 chirality centers created. Since at every step of it, even during the shift, it was trigonal planar, that means that you could have R and S possibilities at each new chirality center you created, and so that's going to be all 4 possibilities. Any questions about that? All right, so that was just to kind of give you a little practice with a ring, because I know you don't like rings still. This one has peroxide in it, so you're starting with a bromine radical. That's the driving feature for this. Your source for electrons is once again the pi bond, and all you care about is where the radical ends up, because radical and carbocation stability are the only issue with all of these reactions. So you want to have the radical on the secondary, so that means that the bromine's going to wind up on the primary by default. There's no option for a shift. That's why I threw this one in here, just to make sure you remember that. And so you look in the next step at what resources you have left over to take care of the radical. The HBr is present in the highest concentration, and you're trying to figure out which one is going to be the better radical, the hydrogen or the bromine. The bromine's going to be a better radical that results, so that's why you're attaching the hydrogen on to create a new bromine radical. This doesn't have any chirality centers. Because you have multiple hydrogens, or the one carbon has multiple methyl groups. Any questions about that? All right, and then G. Pi bond's the driving feature. You can decide between primary and secondary where to put the carbocation. The carbocation goes on the secondary. Once you got the carbocation there, step 3 is watch for a shift. You do have a tertiary next door because you have the option of moving a hydrogen, move that instead of a carbon, because the carbon's what's stabilizing it. If you move the hydrogen over a notch, now you have the carbocation on the tertiary carbon. Then look for what resources you have left over to form a 4th bond, and that's the bromide that resulted from the reaction in the first step. This also doesn't have any chirality centers because you have 2 ethyl groups attached to that carbon. Okay, so when I'm grading, I'm just looking at what you have in that box and what you've circled down here. But maybe draw arrows so you don't get confused. It's a good practice to get into anyway, because like I said, we're going to keep adding reactions, and after a while it gets kind of confusing of, where does the bromine go? Does it go in the primary? No. Just think about radicals and carbocations. All right. I have the mixed IUPAC and the pure IUPAC switched in order. So the mixed IUPAC, no I don't. I did it okay. Never mind. 4S, 5R, 5-tert, butyl, nonane, 4-all. Anything where you have questions about where I came up with that from? And I know you needed multiple ones to label everything on. These are such big molecules. I ended up just putting one on, but on the test I made sure that I put multiple copies of it so that you can label it more clearly. And then the same thing for if you're doing the pure IUPAC, it's just that that group is a 1,1-dimethyl ethyl. No questions? Okay. Wouldn't that be lovely if I made the order match up everywhere? Okay, anyway, the IUPAC is 2-methoxybutane because the OCH3 is a substituent group, and you're saying where that's attached to the parent hydrocarbon. Don't forget that you can turn corners. When you're doing the common name, then the oxygen becomes the focus, and you're saying what substituent groups are attached to it. Any branching is described as sec or tert or iso. So that's a sec-butyl methyl ether because this is a secondary carbon. But don't forget that iso is one where, isopropyl is one where you might get suckered into thinking that that's a sec-propyl because it's attached to secondary carbon, and in theory it could be either, but that one is only called isopropyl. All right, that's all of them, right? All right, I will airdrop this to you, but what else can I do to help you get ready? Oh, bother. Classroom must not be open.
I have a question.
Uh-huh.
So can we be like pretty generic? So like for 2 it says select which vanilla carbon. Will we be okay if we put like more C attached rather than saying hyperconjugation?
Sure.
Oh, okay.
Sure. I don't know if all of these people are in our class. I don't think so. There's a bunch of people who are getting a organic chemistry document who really didn't want one. As far as you guys go, though, did you get it?
Yeah.
Anybody not get it? Open this. As I said, the test is very similar in terms of the type of questions. The types of questions are even in the same order. I just have the molecules different. But if you can do this, you'll be fine. As long as you understand what you're doing and not just kind of like, I know the hydrogen ends up over here somewhere. Just be real methodical going down through the steps, labeling everything. Anything else? Okay, and I have an extra credit question on there too. It's a challenge question. Something a little different. No, I failed at that. I should have put a lab concept question in your study guide so I could put it on the test, but I didn't, so I'm not.
I remember we all like got almost the same answer. It was like 11.5.
No, I think that was the correct answer, and I think everybody had 2.5. Yeah. Just because that's how it was on the study guide, so it's like it's got to be 2.5 again.
It's 2.5. Too bad it's 2.5.
All right, well, if you guys don't have any more questions or any other issues, I don't want to waste your time. Yeah?
Sorry. I'm not sure why I continue for this principle. When it comes to splitting a pi bond and to make radicals, I don't remember which one, so it's like a 50-50 flip, and I feel like I'm missing the principle. When I split the pi bond, I don't know if the bromine radical is supposed to go to the pi bond, or if the pi bond goes. Yeah, exactly, that's what I'm looking at. But like I see them both.
You always draw arrows going from the electron source to the electron deficient atom, because you're showing how electrons travel. The incomplete valence shell is missing an electron, so that's the electron deficient. The pi bond is the source to supply the electron. So that's why you're going from the pi bond to the radical. And then your leftover, you have to show where it goes.
Okay. That makes more sense then.
So you just kind of like using one electron to attach the bromine, and then the other one's just kind of like, oh, I didn't get to go anywhere.
Okay. That makes more sense then. Bromine is incomplete to start with, the other one is getting in position.
So every time you're drawing arrows, it's always going towards an incomplete valence shell or partial positive.
Okay.
Because that's what wants the electrons, so that's why the electrons are going there. I'm showing the electrons are going. Anything else? There are lots of little rules, but at least the rules don't change. So once you got them,